Okay guys, what we're going to have a look at today then, moving on from our last video on ionic structures and our other videos on bonding where we did our dot cross diagrams, is we're going to have a look at covalent structures today. Now, if we think back to our ionic structures, there was only really one type of structure in ionic. That was giant ionic lattices, and we explained why they could conduct electricity when molten in aqueous. We explained the high melting point, we explained the solubility in water. Things are a little bit more complicated when it comes to covalent substances because we have two different types of structure. Okay, and they are giant molecules, giant molecular, and we have what we call simple molecular. Now these two structures, despite both having covalent bonding within the molecules, have got very, very different properties. Giant molecular substances tend to have extremely high melting points, boiling points. Okay, whereas simple have got very low melting points and boiling points. They pretty much tend to be gases at room temperature. Typical examples that you would know would be nitrogen, carbon dioxide, oxygen, water, which is a liquid, fluorine, which is a gas, chlorine, which is a gas, etc., etc. Giant molecular substances then that you need to be familiar with are diamond, graphite. Those are both made up of carbon. Okay, the carbon is just arranged differently in each of those, and they are referred to as allotropes of carbon. Okay, so that's a word that you need to be familiar with. They're both pure carbon, but they have got different physical properties, different melting points, boiling points, hardness, colour. Okay, and those of you who know diamond and graphite will be perfectly aware of that. The diamond is that very clear, colourless, sparkly stone in rings and cutting tools, whereas graphite is essentially the colour of pencil lead and the structure of pencil lead. Okay, so let's have a look then. And the other one is silicon dioxide. Those are the little colourless, glassy looking crystals that you see whenever you are on the beach in sand. Okay, so we need to be able to have a look at these structures and use these structures to explain the properties. Now the first one that we look at, we will go into giant structures. Okay, so our diamond, our graphite, etc. And the first one that we will have a look at then is our diamond. Okay, and we'll have a look at the arrangement of the carbon atoms in diamond. So if we have a look, this is a little makeup of the structure of the carbon atoms in diamond. Okay, I'll just put that into focus. Hopefully you can see that pretty well there. Okay, so if we just take one little unit of this. Okay, so each of the black dots then that we have here is a carbon atom. Each of the black lines then is a covalent bond holding one carbon atom to another. So if we concentrate just on this little carbon atom here, okay, let's have a look at it first of all. Well, firstly, it has got 1, 2, 3, 4 bonds to it. Okay, now that means that goes on throughout the entire network of this giant molecule. We're talking millions and millions of carbon atoms in one little diamond, all joined in this huge, big, ongoing network of carbon attached to 1, 2, 3, 4 other carbons. If we take this one as well, 1, 2, 3, 4 other carbons. Okay, now what does that give us? Well, these carbon-carbon bonds are very, very strong. If you think of carbon, when it bonds, carbon has got an atomic number of 6, which gives it 4 electrons in its outer shell. So carbon is 2, 4. That means when carbons attach to each other, they only have two shells. So the bond from one carbon to another is very, very short. And when bonds are very, very short, they tend to be very, very strong. So the bonds within this diamond are very strong. That's the first thing. The second thing that we need to take into account is the actual arrangement of these atoms to each other. Okay? And they are in what we call in chemistry a tetrahedral arrangement. Okay? So, in other words, if I have a carbon here, I have another carbon above it, and then we have this sort of three-dimensional setup. Okay? Which leads to this tetrahedron type shape. Okay? And if we have that tetrahedron type shape, what we get then is a structure which is extremely difficult to compress. It's very, very difficult to press down on. If you think of your Tetra Pak, your old milk cartons, the reason they were called a Tetra Pak, they were a similar sort of a setup because in transport they were very difficult to compress, very difficult to squash, which is obviously an ideal property of the structure of a milk carton. So that's how these things are structured, and that's why diamond then ends up being so hard, because you have this tetrahedral arrangement of the atoms. They are also very strong bonds in there because they're such short bonds. And the combination of those two things make it very difficult to compress, so it's very hard. That's why it's using cutting tools. Okay, the ends of drills where people are cutting through rock and very, very hard structures. And on top of that, the bonds themselves are extremely strong. There's no point in having a tetrahedral arrangement if the bonds inside something are very, very weak, because it will not be as strong as you would like it to be. Okay? Now, so it's difficult to compress and it's very, very hard. The other thing is, because these bonds are so strong, you're going to have very high melting point. Okay, it takes huge amounts of energy to break the bonds. Okay? Now, high melting point, because we need lots of just E for energy to break those bonds. And the other thing is, remember, it's a giant structure. This goes on for millions and millions and millions of atoms. So in order for me to break and melt this, I've got to break all these many millions of bonds that are in here. And that requires huge amounts of energy. The melting point of diamond is actually well over 3,000 degrees Celsius. So it's huge. If you think that water melts at 0 degrees Celsius, okay, well, diamond doesn't melt until well over 3,000. Let's look at the ability of this thing to conduct electricity. Well, we saw in the last one that ionic structures could conduct electricity because they had free ions. And the one that we looked at, they had free sodium and chloride ions. Well, this is covalent, so there are no free ions. Metals can conduct because they have free electrons. Well, if we look at this, carbon has got 4 electrons in its outer shell, and we have already established that every carbon is attached to 4 others. That means the 4 electrons from each carbon are used up in bonding. So it has no free electrons. So this substance cannot conduct electricity. It's an insulator. Okay? So that's pretty much all about diamond. Okay? It has got a very high melting point. It has got a very strong, rigid, hard structure, difficult to compress, and it doesn't conduct electricity. Let's move on then and look at the other allotrope of carbon, which you need to be aware of, which is this time graphite. So if we have a little look at our graphite, we will see that despite the fact that both of these substances are carbon, okay, they are extremely different in the way they behave. So there's a sort of a a way you could see carbon if you had some sort of magic microscope, and if you can just about pick it up there, it is in layers. And if we take a subsection of this and we blew it up, we would see it is most certainly in layers. Now, it is very, very different than diamond, despite the fact that it is made up of carbon atoms. The black spots are carbon atoms, and the lines joining the black dots together, the black balls together, the carbon atoms, are again covalent bonds. So why is it different? Well, let's have a look. Firstly, if we look at it, it's in layers. These black lines here joining the layers or between the layers are not covalent bonds. These are called weak, and that's key, van der Waals forces. Now, that is very, very important that you understand that, because weak van der Waals forces mean that the attractions between the layers, so if I just draw layer, 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 and there's my van der Waals forces holding the layers together. These forces are very weak and they will break. So in other words, if I apply a force in that direction, the layers will simply slide past each other. Think of your pencil. Okay? If I take a pencil and I put it onto a piece of paper, what happens? Well, the layers slide past each other, and I leave a layer of carbon on my piece of paper. So this structure here, despite the fact that it's giant covalent, despite the fact that it is made up of carbon atoms which are joined together by covalent bonds, within the layers it's joined together by covalent bonds. Between the layers we have these weak van der Waals forces, and that means the layers can slide past each other. Okay, if we look between or within the layers here, okay, so if we blow that up again, okay, we can see that these are covalent bonds. These dotted lines, okay, those are our weak van der Waals forces, and therefore these layers will slide past each other. The attractions within the layers to break these carbons away from each other, here and here and here, etc., are extremely high, because again these are carbon-carbon bonds, very strong bonds. Okay, so this substance is soft, the layers slide past each other very easily. Now let's have a look at the ability of this to conduct electricity. Well, let's take this carbon here as our sample one. It's attached to 1, 2, 3 other carbons, and if we remember from diamond, okay, if we remember from diamond, we said that diamond could not conduct electricity because diamond had no free ions. Well, this again is covalent, so it has no free ions. We also said that carbon could not conduct electricity in form of diamond because it had 1 carbon attached to 4 others, and all the 4 electrons were therefore used up in bonding. But in graphite, there's only a carbon attached to 3 others. So in other words, only 3 of these 4 electrons are used in bonding, which means we have a free electron. And graphite can, in fact, conduct electricity, because that free electron that I've spoken about can be found between these layers. Okay, and that means that there's my electrons moving around, they're in between the layers. Electricity can flow between the layers. Okay, so electricity will flow between the layers, and this can conduct electricity. It's probably the only known metal on your syllabus that can conduct electricity. In fact, I'm pretty sure it is the only known metal on your syllabus that can conduct electricity. Okay, let's have a look then finally at the melting point of this. Well, remember, this is a huge ongoing network, and we're talking millions and millions and millions of carbons per layer. Now, in order for me to melt it, it's not good enough just to break these dotted lines, these intermolecular forces which are weak. Okay, I have to break the covalent bonds between the carbon atoms to get free carbon atoms. It's no good just getting free layers. Okay, so therefore this has a very high melting point, because the energy required to break the bonds between the carbon atoms is huge. And again, this melted well over 3000 degrees Celsius. Okay, so that is two structures, two giant covalent structures, and you should be able to use them now to explain why they can or cannot conduct electricity, why they are or are not hard or soft, okay, and why they have such high melting points. Now we're going to look then at the second type of structure within covalence, which is this structure which we call simple covalent. Now, if you think of what you did with your dot cross diagrams, guys, those substances were all pretty much simple. They were all simple covalent. So you will have heard of a lot of these, like carbon dioxide, water, oxygen, ammonia, methane, okay, nitrogen. These are all simple covalent. Now, all of those are gases at room temperature except water, which it boils at 100 degrees Celsius. So hopefully you're all now able to appreciate that simple covalent substances have very low melting and boiling points. Okay? Well, let's have a look at the reason for that. Okay, and we'll have a look at something very simple like molecules of, let's say, molecules of water. So molecules of water are H2O, and they're bonded like so. And if you remember your dot cross diagrams from previously, that's the bonding in a molecule of water. Okay, now, so what is the significance of that? Well, the significance of that, very simply, is that we don't have this huge, big, ongoing network. We have a little water molecule here, another one over here, another one over here, etc., etc. And they are attracted to each other. There is attractions between the molecules which hold them together. Otherwise, water would not be a liquid, nor could it be a solid. But these attractions are very weak. Okay, and they are called weak intermolecular forces. Okay, some of them are van der Waals. These are not. These are actually hydrogen bonds, but the majority of them are van der Waals forces. But they're very weak. So if I want to melt or boil water, I will have to get separate water molecules. So in order to do that, all I need to do is to break these little attractions between the water molecules. And that gives me now completely separate water molecules. And the energy needed to break those attractions that were between the water molecules are very, very weak. The same goes for all simple covalent structures. The energy needed to break the weak intermolecular forces is very weak. Whereas in diamond and in graphite, remember, I was having to break very strong covalent bonds. That is no longer the case. If I broke the covalent bonds in water, I would end up getting hydrogen and oxygen separately. Okay? What's wrong? So if I was to break the strong covalent bonds in water, I would end up with hydrogen and oxygen. And that would not be melting or boiling, because that would be a chemical change. Melting, remember, is taking solid water and turning it into liquid water. Boiling then turns that into gaseous water. I do not ever break the covalent bonds and turn it into oxygen and hydrogen. So, simple covalent structures have got very low melting points and boiling points. If we go, because they have weak intermolecular forces, if we go back to our bonding diagram of water, okay, and I'm just using water as my example, you need to apply this to all covalent structures. Okay, in here there are no free electrons. Oxygen 6 electrons are all used in bonding. Hydrogen 1 electron is used in bonding. So this does not conduct electricity. Okay, And the reason is because it has no free electrons. Graphite had free electrons, nor does it have free ions. Well, that should be common sense because it's not an ionic structure. So it does not conduct electricity. Okay guys, that is pretty much what you need to know about giant and simple covalent structures. Remember, diamond, graphite, silicon dioxide are your giants, and the covalent, simple covalents are pretty much all the others, those little ones you did dot cross diagrams for. I hope that helps, okay, and is useful for your revision.